All right, everyone. Welcome back to the notes. This is the last page of section 13.3. This is the second time recording these notes, or just this page, because apparently the microphone was not on during the first recording, so I get to do this again, so that's fun. It's always fun when you're doing math. So, the first one. So, the circle that lies in the osculating plane of C at P has the same tangent as C at P. Lies on the concave side of C, toward which, our unit normal points, and has radius rho is equal to 1 over kappa, which is, just the reciprocal of the curvature. And it's called the osculating circle, or the circle of curvature of C at P. It's a circle that best describes how C behaves near P. It shares the same tangent, normal, and curvature at P. Same tangent, same normal, and same curvature at P. So I'm just going to, draw real quickly, what this represents. And so say I have a curve. The osculating circle is just the circle that barely touches our curve. All right. And when it touches our curve, it's going to, what's going to happen is there's going to be a circle that's going to be formed. And when I say barely touches, like just barely touches. So, a lot of others say, it just kisses the curve. And why I would say just, kisses the curve is because that's where, we get osculating circle. Kiss in Latin is osculum. And so therefore, that's why, we get the osculating circle. So it just barely touches. And so it's going to be on the osculating plane as well, because it is going to be made up by the tangent. So its tangent is going to be the same as the tangent of our curve at that point. So that's going to be the same. So say we have the same tangent. All right. And the normal vector is going to... So this circle is not very centered, but if it was a better circle, all right, that normal vector, unit normal, is going to be pointing in the direction of the center of that circle. All right, so say I drew a better circle. Well, that is not even close to like the center. So I'll just say the center of that circle is where's the unit normal is either going to go through, or it's point, or it could be like a little bit shorter if we wanted it to be, and say, the unit normal is going to go that far, and then, there's the center. All right, but that unit normal is going to be pointing in the direction of the center of our circle. And there's one more thing I wanted to add to this. So we're pointing to the direction of the center. And the radius is always going to be given by a curvature. It's just going to be the reciprocal of whatever our curvature is. And the reason why that is because, this osculating circle is going to be defined by how, why the curve is at the point. If it's very curvy at that point, so say, the point was very curvy, our circle is going to be much larger because... All right, it has a bigger curve. In fact, we have a smaller curve, we're going to have a smaller circle at that point. All right, so that's what the osculating circle is. So now let's go ahead and solve and find the osculating circle at the values given, for example, 8. So problem, this is part 2 in the text. Find equations of the osculating circles of the parabola y equals 1/2 x squared at the points 0, 0, and 1, 1/2. So that A should have went right there. So what we're going to do is we're going to go ahead and find our derivatives. So y is equal to, let's go ahead and do y prime. Y prime is equal to x. Y double prime is equal to just 1. And the reason we did that is because we know how to find curvature pretty easy when it's just, given to us in terms of one function. And so if you recall... what our curvature for, just having that one function is, kappa of x is equal to the magnitude of the second derivative of our function over 1 plus the derivative squared to the 3/2. And that's from last class. And so, again, we want to use this equation for curvature when we have, our function as, x, y of x. So... what we're going to do is we're going to go at 0, 0 first. So the curvature at 0, 0, the curvature at 0, 0 is just going to be kappa of 0, which if I plug in, I'm going to get 1 over basically 1 to the 3 halves, which is going to give me 1. So the curvature at 0, 0 is just going to be 1. And so our osculating circle at that value is going to have, if I do my rho, I want to do a rho better than that. Let me just look at it. Our rho is equal to just the reciprocal of that, which is 1. So there's our radius. So we have a radius of 1. And our center, if we're at 0, 0, and our center is just going to be a distance of 1. So 0, 1. Therefore, our equation, I'll use that symbol. Our equation is just going to be x squared plus y minus 1 squared is equal to 1 squared, or just 1. So there's the equation of our circle for the first value. All right, our second is let me highlight this to 0, 0. Our second is going to be, what about the point 1 and 1/2? So finding the curvature is going to be the same. We're going to put it in to our equation. So curvature now at 1, that's going to give me 1 in the numerator, and then in the denominator 1 plus 1 squared to the 3 halves. It does not look like a 3 up top. To the 3 halves. So therefore, we're going to get 1 over 2 square roots of 2. Because we'll have 2 to the 3 halves power. And so we get 2 square roots of 2 in the denominator. All right, now, if that's going to be our curvature, then our rho is equal to just 2 square roots of 2. So that's our radius. 2 square roots of 2. That's how long our radius is. All right, so now that we found that, let's go ahead and think of the slope. So what about the slope of our point? So if we take the slope, again, our slope is going to be given by y prime of x. So if our slope, so f prime of 1, our slope is going to be, we're just using our derivative there. So we just plug in, so let me change back to the pen. Our slope is 1. Now we want the slope of the normal line to this. So now the slope of the normal line is going to be all right, the slope of the normal line is going to be negative 1. All right, how do we know this? And this this is back from calculus, 1, where we talked about finding the tangent line, then finding the normal line, and always the tangent line was just the negative reciprocal of whatever we had as our slope for the tangent line. So this is where our normal line comes from. But we want the unit, so what we want is we want the unit normal. So what I'm going to do is I'm going to go to the unit circle to find this. So this one's a little bit more difficult than a normal one. We're going to go to the unit circle to find it, and I'm just going to go ahead and take, if I have a slope of 1, I'm going directly in between. If I have a slope of negative 1, I'm going directly between in the second quadrant. So this gives us 2 over square root of 2. Square root of 2 over 2. Both positive for y and negative for x. But I'm going to say negative 1 over square root of 2 and 1 over square root of 2. All right, you could keep that as negative square root of 2 over 2 and 2 over square root of 2 for both the x and y. I'm just going to keep this way because I know that there's going to be a few things that cancel out. So that's the unit normal. So the unit normal is just now the vector negative 1 over square root of 2 and 1 over square root of 2. All right. Now, I want to find the center. So if that's the unit normal, how to find the center is, okay, well, what point are we starting at? So we're starting at 1 and 1/2. And what we want to do is we want to find out, okay, well, what's the distance, of the radius? So what we're going to do is we're going to multiply by 2 square root of 2. That's the distance of the radius to point to the center of the circle. And the center is in the direction negative 1 square root of 2, 1 square root of 2. And we needed the unit normal to actually multiply to get us here. And so we get 1 plus negative 2. So that's going to be negative 1. When we multiply, and 1/2 plus, looks like 2. So we're going to get 5/2. So there's the center of our circle, our osculating circle. So we have the center and we have the radius. So therefore, what we can do is write our equation for a circle. So it's just going to be x plus 1 squared plus y minus 5/2 quantity squared is equal to our radius, which is 2 square roots of 2. But if we square that, it's just going to be 8. And so there's the equation of our osculating circle at the point 1 1/2.